Okay. So continuing the theme of asking like what we can do with these multi-calibration algorithms, today I want to think about multi-calibration as something you would want to do explicitly because what you care about is accurate prediction. And the hope is that if you have a way of training predictors that are a little bit accurate, you can use multi-calibration to combine them into predictors that are really accurate. Okay, so we're going to be viewing multi-calibration as what is known in like the machine learning literature as a boosting algorithm. We want to take a learning algorithm that can do like a little bit better than sort of trivial prediction and turn it into a learning algorithm that can do optimal prediction. Okay, so that's the goal. Right, and just to like reflect on this a little bit, we know that like multi-calibration doesn't harm accuracy, at least as measured according to like squared error, right? Like in all of the algorithms we've given so far, squared error was like the potential function. Every update would decrease squared error. And so we always had the promise that if you took some arbitrary model and then ran it through one of our post-processing methods to make it multi-calibrated, it wouldn't be any less accurate. And if you actually had to patch things up a lot, if the algorithm ran for many iterations, it would be substantially more accurate, but we never had the promise that the algorithm actually would run for very many iterations. So it might be that, multi-calibrating doesn't get you something much more accurate. Okay, and it might not if the sets with which you want to be multi-calibrated with respect to have little to do with the prediction problem, right? Like consider the sort of simple running example of predicting rain. You could be regular old calibrated without being accurate at all, just by predicting every day the base rate of rain. If I'm in a rainy place, it rains, on 30% of days, I could predict 0.3 every day and I would be calibrated. And if I then said, okay, well, that's no good, I want to make sure you actually learn how to predict rain in an informative way, you might hope, well, okay, if I just sort of pile on different sort of subsets of days and ask you to be multi-calibrated with respect to all of them, that maybe the only way you could like do that is by sort of making accurate predictions, informative predictions. But if I just define uniformly random subsets of days that have nothing to do with meteorological conditions or anything like that, then likely the base rate of rain on any one of these random subsets of days will also be about 30% because I just picked them at random. And so multi-calibration with respect to this random subset of days isn't especially accuracy promoting either. I can still get away with just predicting 30%. Okay, so the question is, when is it that the only way to be multi-calibrated with respect to some collection of functions is to be accurate? And like we sort of know off the bat that the answer is going to have something to do with the relationship between that subset of functions and the prediction task. And that's what we're going to try to untangle in this lecture. Now, along the way, we're going to generalize multi-calibration from what we've been talking about so far, which is with respect to groups, to multi-calibration with respect to real valued functions. There's a natural generalization. We'll see what that is. And that's going to be useful for us in this lecture, but also the next two lectures are going to involve sort of applications of multi-calibration for which we really want to be able to talk about multi-calibration with respect to real valued functions. So that's something we're sort of introducing along the way in this sort of characterization of when multi-calibration implies accuracy here, but this is really going to be the sort of notion of multi-calibration that will be useful for us going forward. Okay. So let's first like think about what that means. Like we sort of know what multi-calibration means with respect to groups. It's sort of some intuitive thing, and it really seems like it's using the fact that we have groups in some crucial way, right? Multi-calibration with respect to groups is saying, look, I want to be calibrated not just overall, but also on, like the restriction of the distribution to people who have some particular set of features, to some subset, some group of the data. Okay, so the first thing to think about is like, what would it even mean to be multi-calibrated with respect to some like real valued function? Okay, so recall that, we said F is multi-calibrated. I'm going to mean perfectly multi-calibrated for now. You know, alpha is 0, and then we'll talk about approximation terms. F is perfectly multi-calibrated with respect to some collection of groups G if for every group in G and for every prediction that the model might make, for every V in the range of my model, when I look at the expected difference between Y, the actual label, and F of X, my prediction for the label, and I'll look at this expectation not just marginally, but conditionally on two things. Conditionally on X being a member of the group, and we've traditionally represented that by having little g be an indicator function for the group. So little g is really a function that takes value 0 or 1, and we're conditioning on g of x equals 1. We're also conditioning on being in some particular level set of this predictor, f of x predicting v. Right, conditionally on both of those things, this should be 0. Right, this is what perfect multi-calibration means. It means that our predictions are correct on average, they equal the labels, conditional on membership in the group, and also conditional on the value of the prediction. Right. Okay. So like, you know, we're conditioning on g of x is 1. So it seems like important here that g of x is like a binary indicator function. But let's just observe that at least for perfect multi-calibration, there's just like an algebraically different way that I could write down this exact same condition. Right, instead of conditioning on g of x equals 1, I could just write, and this is, you know, completely mathematically equivalent, I could write that the expected value of g of x times y minus f of x conditional on f of x equals v, I could ask that this be 0. Right, and it's the same thing when at least I'm asking that it be exactly equal to 0, because you know, like instead of, you know, like integrating or summing up over only those parts of the distribution for which g of x is 1, I'm integrating or summing up over all of the distribution. It's just that I'm like zeroing out the contribution when g of x is 0, and I'm counting only those parts when g of x is 1. Right, so like this is calibration, this is multi-calibration, exact multi-calibration with respect to groups, which are binary indicator functions, and this is exactly the same condition. But observe that this condition makes sense to ask for, even if g is not a binary indicator function, even if g is some arbitrary real valued function, just some like regression function mapping x's to like the real numbers. Right, like syntactically, it sort of doesn't really make sense anymore in this form, but in this form, this is a condition that is sensible to ask for when g is some arbitrary real valued function. Right. Okay, so, you know, this is going to be the observation that motivates the definition of multi-calibration with respect to real valued functions. And what we're going to note is that it's not like some totally new condition. It is a generalization of multi-calibration from, you know, defined with respect to groups. You know, multi-calibration, as we've studied it up till now, defined with respect to groups, is just a special case where these real valued functions happen to be the indicator functions for groups, but you can define it more generally. Okay, so what do we mean multi-calibration with respect to real valued functions? So, you know, fix a distribution, your favorite distribution. As always, over labeled examples. Fix a model. and fix an arbitrary collection I'll call it H now rather than G, now that these no longer need to be groups, an arbitrary collection H of real valued functions. By which I mean the functions little h in this group, they can be like arbitrary mappings from the feature space to the reals. They're no longer group indicator functions necessarily, they could be. And we say that F is alpha approximately multi-calibrated with respect to H and D if for every single one of the functions little h in this set, and for every, for every single one of the functions h in this set, we have a bound on like the equivalent measure of our L2 calibration error. So I'll give like the L2 definition. Just as before, you could give like an L1 or an L infinity definition, but the L2 one is sort of going to be convenient and strong. So we want that our L2 calibration error on H, which is just the sum over all of the level sets, all of the level sets in the range of our predictor, of the probability that we make a prediction in that level set, times the expected value of h of x times y minus v, conditional on f of x equaling v, all of this squared. We want this to be less than or equal to alpha. Okay, makes sense. So this is the same as the definition for multi-calibration we have grown to know and love when H is actually a collection of group indicator functions, binary group indicator functions. It's just that when we write things in this way, this is now a sensible criterion to ask for, even when H contains real valued functions. Okay, so it's the same thing, right? It's the average like squared calibration error. It's like the average difference between our prediction, which is v, conditional on f of x equals v, and the label, weighted by g of x, which is the same as like saying conditional on g of x when g of x happens to be 0 or 1. Okay, so that's the definition, and it should be familiar and lovable and stuff. Do you guys recognize it? Does it seem like, am I justified in using the word like multi-calibration for this new definition? You guys think? Yeah. Okay. So, okay, so now I want to be able to ask the question, oh, yeah. That's right. Yeah. So like, and this is where sort of the difference between like conditioning and, multiplying by G is different. There's no difference when we're asking for it to be 0, but when we're bounding it, there's some difference, right? So like, really, what is the conditional expectation of y minus f of x conditional on g of x is 1? Well, it's actually the expectation of g of x times y minus f of x divided by the expectation of g of x, which when g is just an indicator function is just mu of g. Okay, so yeah.
So is this new definition like means the correlation is 0, like correlation between x and y minus f?
Yeah, something like that. Maybe it's like a little closer to covariance, but yes. Good. Okay, and so like to set things up, so these are, so now everything's a regression function, right? Like before, like the G's were somehow, classification functions. Are you a member of the group? Now, but F was a regression function. F here is a regression function. Now the H's are regression functions as well. And so the kind of question I want to get at is, suppose I have some learning algorithm that can like learn functions in H, but so maybe like H are like linear functions. So I have like a PhD in economics, and so I've learned about linear regression. And no offense. Yeah, and a PhD in statistics. I'm making enemies. So now I know. Right. So whatever. I've studied for years and years and years. So I know about linear regression, but like on my problem, like linear regression doesn't do so great. I would like to do really well. So the question is, I know how to learn simple things like linear models. Is there a way that I can combine them in such a way to learn like complicated things, maybe optimal things? So the question I would like to ask is, if I have the ability to solve regression problems over this class H, like I can solve the problem minimize squared error over anything in H, so literally linear regression if H is the set of linear functions, when does that ability allow me to learn Bayes optimal predictors? Okay. And so the way we're going to ask this question is we're going to, first of all, give an algorithm for multi-calibration with respect to H. We're going to say, look, suppose you can solve regression problems over H. We're going to take that ability and show that you can sort of use that as a subroutine a small number of times to solve, to become multi-calibrated with respect to H. So the algorithmic task, so maybe to reflect, our algorithms for multi-calibration so far for groups, right? They've sort of had this step where they need to like enumerate over the groups. You have to find, some group to run this patch operation on. You have to like check all of the groups. And that might take a long time if there's like continuously many of them, as like there might be if we say H is like the set of all linear functions. So we're going to need to talk about some way in which we can access hypotheses from H. And a natural assumption is to assume that we can solve squared error regression problems over H. Okay. And the question is, okay, and so the first thing we want to show is that the ability to solve squared error regression problems over H is sufficient to be multi-calibrated with respect to H. We'll give an algorithm that only needs to, that's the only computational problem it needs to solve, squared error regression problems over H. And then we'll show necessary and sufficient conditions for when multi-calibration with respect to H implies Bayes optimality. Okay, so that's the plan. Yeah. We do not, but this will, like we will talk about bounds on little h. So it's like one observation is we're not going to be able to give, if h is the set of linear functions, for example, if h is in the class, so is a million times h, because linear functions are closed under, linear transformations. So we're not going to be able to like uniformly bound this kind of thing for all like linear functions, because if I have alpha calibration error for h, I have a million alpha calibration error for a million times h. So when we speak of the bounds we can get, we are going to have to take into account the norm, some norm of h. But it'll also be convenient for us to be able to talk about classes like linear regression. Okay. So in order to understand this question, I want to understand some relationship between failure to being multi-calibrated with respect to h and the ability for h to make, I want to understand a relationship between the following two things. The failure of my model F being multi-calibrated with respect to h, and the ability for me to improve the predictions of F with respect to some function h. Okay. Okay. And sort of there's going to be a two-way relationship. It's going to be roughly as follows. Suppose I have some model F. I can look at the level sets of my model F. Okay, on the level sets of my model, by definition, I am making like a constant prediction. Like that's what defines the level set. I'm like restricting to a place where my model predicts some constant V. If my model's calibrated, it's even like the best constant prediction I could make amongst the set of all constant predictions there, because it's the expected value of the label on the level set. But, you know, it's possible that if my model is like super dumb, like I'm predicting 30% chance of rain every day, you know, I'm making the best constant prediction I could make on this level set, but maybe I could do a lot better than if I were just predicting a constant. Okay. So the first thing we're gonna do is we're gonna say, okay, well, suppose there's some h, little h in my class, big H, that can predict just a little bit better than a constant on a level set. This is like a pretty weak ask for a predictive task. Like when we care about when we care about squared error, the best constant prediction comes from just like predicting the mean. Like you can always just do that. So suppose H can produce a prediction that's like just a tiny bit better than a constant prediction. Then it will, as we will show, it will be the case that we cannot be calibrated on this function H. We'll have some violation of the multi-calibration condition on H. Okay. And then, like we'll show the other direction. If we have a failure to be multi-calibrated, if we fail to be multi-calibrated with respect to some function H, then it must be that there's some level set of our predictor for which we can predict using H a little bit better than a constant. Okay, and this if and only if condition is going to form the core of our characterization. Okay, so here's the first direction. Fix a calibrated model. F. Okay, so not multi-calibrated, just calibrated. I mean that if I restrict attention to every level set, then every level set V, then the label mean on that level set is actually V. Okay, calibrated model. Suppose that there's some prediction in the range of this model. And there's some model H in my class of models, like there's some linear regression function, such that when I look at the difference between the squared error of my predictor and the squared error of this function H, conditioned on being in this level set, that this difference is at least alpha. Okay, so there's some level set such that there's a function in H that gets an improvement of alpha in squared error compared to my predictor. And remember, since we're looking at a level set of my predictor, this is actually just the prediction of the best constant. The best constant, it's constant because it's a level set, the best constant because it's calibrated. Okay, so it's not asking a whole lot of H, it's just asking that we do like a little bit better than constant prediction. Okay, it's saying if there is such an H that lets you improve on squared error on some level set by alpha, then you must fail this multi-calibration condition with respect to H. Then it's got to be that the expectation of H of X times Y minus V, given that F of X is V, is at least alpha over 2. Okay, so it's like, this thing is supposed to be small, but if I can improve on the squared error of a prediction with something in H, then the thing that's supposed to be small is actually big. Okay, is the statement clear? Okay. So how come? Let's see. Let's start with this thing. We want to argue that this thing is big. All right, so we've got the expectation of h of x times y minus v, given that f of x is v. And I can just write that as well, the expectation of h of x y, given that f of x is v, minus v is a constant that can come out of the expectation, minus v times the expectation of h of x, given that f of x is v. Right. And, you know, it might be nice if these numbers were multiplied by 1/2. That would be nice, but I can't just multiply stuff by 1/2. Like, what the hell? That's cheating. So if I want to do that, I have to also multiply everything by 2 again. So like, make everything come out the right way. Okay. Then I'm going to need more space for the next line. And we'll do the following like dumb maneuver. We'll say, okay, I can always just copy over everything I've written so far. And I'm trying to upper bound this quantity. And so I can like subtract off any non-negative number that I like, because subtracting off non-negative numbers will only make the quantity smaller. So I'll do that. I'll subtract off the expected value of h of x minus v squared, given that f of x is v. Okay, like the square of anything is non-negative, so I can like subtract it off, and I've only made the quantity smaller. And the reason that's convenient to do is because it'll induce a whole lot of cancellations, right? So I'm going to have, in particular, like a cross term that's going to be plus 2 times h of x times v. You know what? Rather than multiplying by 2 on the outside and multiplying by 1/2 on the inside, let me do it the other way around. Multiplication is commutative, so I can do it this way too. Okay, so I'm going to have like a cross term that's like 2 times h of x times v, and that's going to cancel out this annoying cross term here, 2 times h of x times v. Okay. So when I do that, what I'm left with is 1/2 times the expectation of 2 h of x y, that's this term, minus h of x squared, that comes from here, minus v squared that comes from here, and the cross term that came here canceled out to this middle term.
We're missing a 1/2. Oh, no, it was just the bracket. Sorry, the bracket is, sorry.
There's a,
Discounted brackets.
yeah. Good catch. Okay, so it's just this expectation, all conditional on f of x is equal to v. Okay. And now I'm going to do another dumb maneuver, which is that basically I'm going to add a copy of v squared, and then I'm going to subtract off a copy of v squared. And I'm going to use the fact that, remember we said f was calibrated. We haven't used that yet, which means that the expected value of y on this level set is v. Okay, so when I add v squared and subtract off v squared, actually I'm going to add and subtract off vy, which is the same thing because f is calibrated. Okay, so I can write this as 1/2 times the expectation of 2 h of x y minus h of x squared minus 2 vy plus v squared. Conditional on f of x equals v. And here I'm using the fact that the expectation of vy is v squared because of the calibration condition. Okay, so I've just added and subtracted the same quantity, and I've used the fact that f is calibrated here. Well, this, now that we've massaged things into this, right, we can write this now as the expected value of v minus y squared minus h of x minus y squared. Conditional on f of x is equal to v. Okay, if you like expand out these squares, you get what's up here. And this is the quantity that we assumed was at least alpha, right? This is the improvement in squared error that h gets on this level set compared to f, which is just predicting v, the constant on this level set. So by hypothesis, that's at least alpha. And so this whole thing is at least alpha over 2. Okay, so this is saying if we've got some candidate function f, and on some level set, f's predictions are not so good, and we can certify that by demonstrating some function h that can predict even better on that level set. Well, the only way that can be true is if we were somewhat miscalibrated with respect to h. Okay, so it's a connection in one direction, showing, you know, if it's possible to improve the prediction with h, then you can't be like super calibrated with respect to h. Clear? Okay. So that's one direction, but the connection goes in both ways. Okay, so I want to prove the other direction as well, that sort of says, okay, you know, like if you're not super calibrated with respect to h, then it's got to be that there's some way to improve your predictor on at least one of the level sets using h. So here's the lemma in the reverse direction. Fix a model F. Okay, again, it's a regression model from features to real numbers. suppose there exists some level set, some v in the range of our function. And also some little h in our class big H, such that when we look at our multi-calibration condition with respect to h on this level set, when I look at the expected value of h of x times y minus v on this level set, this is at least alpha. Then for this other function h prime that I'm about to construct, which is just defined as h prime of x is equal to v plus eta times h of x, where eta is the following constant, alpha squared over the expected value of h of x squared on the level set. Then h prime predicts better than f on this level set by a non-trivial amount. Okay, if I look at the expected difference between the squared error of f on this level set and the squared error of h prime on this level set, then this is not nothing. It's at least alpha squared over the expected squared magnitude of h on this level set. Okay. And notice now we're getting a term that depends on like the scale of h, right? And this is sort of necessary, right? Because, you know, again, if we're talking about h, the set of linear functions, if I'm like alpha miscalibrated for some function h, then I'm like a million alpha miscalibrated for some function a million times h, which is also a linear function. And so like you couldn't, it would be like way too much to hope for to sort of say, okay, for any function h that has alpha miscalibration, you just like can improve the error directly proportional to alpha, because then I could like get, you know, negative squared error. I would just take a million h. And so the improvement is sort of large if h has small magnitude, and the improvement is small if h has large magnitude. And this is the kind of scaling that is just like unavoidable if you've got some class of functions that is like closed under linear transformations, for example. Okay, is the statement clear? Okay, so let's just, you know, like do it. So we want to show that this is big. So let's start here. So we're interested in the expected value of squared error of f minus the squared error of h prime. On a level set. And, you know, on this level set, we know these aren't like totally mysterious quantities. We know what f is, it's v. We know what h prime is, so let's just write down what it is. All right, so just plugging things in, you know, on this level set, f of x is always v. This is just v minus y squared. And h prime of x is always v plus eta times h of x. Okay, and now we can expand out terms. So we, okay, we've got v squared. We've got minus 2vy. We've got y squared. We've got v plus eta h of x squared. We've got 2y times v plus eta h of x. And we've got minus y squared. Okay, and now we're starting to get cancellations. We've got like a y squared and a minus y squared. We've got some other cancellations, so we can just cancel and consolidate terms. What is this? Well, it's the expectation of, I guess the v squared cancels out with this v squared. The 2vy cancels out here with this 2vy. So a lot of things cancel out. And we're left with 2y eta h of x minus 2v eta h of x minus eta squared times h of x squared. And we're taking the expectation of this again all over this level set. And I can rewrite this as the expectation, just combining these two terms of 2 eta h of x times y minus v minus eta squared times h of x squared. Okay. Now, by assumption, the expectation of h of x times y minus v, this is our multi-calibration term, which is here, is at least alpha, right? So this is at least 2 eta alpha minus eta squared times h of x squared times the expectation of h of x squared on this level set. Okay, but how did we choose eta? We chose eta so that this would be half of this. That was how we solve for eta. And so this is just equal to eta. Okay, so this is equal to eta, which we chose to be alpha squared over the expectation of h of x squared on the level set. Okay, which is the statement of the lemma. Okay, so we have the connection in both directions. If you can improve on some level set with one of your functions in h, then you are not multi-calibrated with respect to h. On the other hand, if you're not multi-calibrated with respect to h, you can improve on one of the level sets using one of your functions in h. Okay, actually not quite. I said that more symmetrically than the statement really is, because if you can improve with one of your functions h, what we showed is that you are literally failing the multi-calibration condition on h. On the other hand, what we proved here is that if you're failing the multi-calibration condition on h, then you can improve on one of the level sets, not necessarily with h, but with this h prime. Okay, so not quite symmetric. But it is symmetric for a very nice well-behaved class of functions, which are the functions that are closed under affine transformations. Okay, because what is H prime? It's nothing but an affine transformation of H. We are multiplying by and adding a constant. Yeah. I'm not sure.
C times alpha cubed over 7 is already an alpha. Then you're subtracting out theta squared, you get alpha to the fourth. And then the denominator you get it as well.
How about now? I think this is right. Because then we've got, what's eta times alpha? 2 times eta times alpha. It's 2 alpha squared over the expected value of H squared. And then what's eta squared? It's alpha squared over the expected value of H squared squared, but multiplied by the expected value of H squared. And so we have twice this minus one of these. It's the expectation of H squared. And then eta itself is squared over here.
Oh, I didn't square it.
All right, but good point. There was a what is a typo when you do it on the board? A choco. Anyways, shouldn't have been squared.
I think why H prime an improvement compared to H?
What do you mean an improvement compared to H? What we proved is that the thing that decreases squared error on this level set of F is H prime.
Saying that from H we can do an H prime, which is like does better on that level set, right?
Yeah.
Why? I can see from the situation.
This is why. Or maybe I'm not understanding the question. The claim is that if you build H prime in this way by just taking H, multiplying it by this constant, and then shifting it over by this constant, then it decreases squared error compared to F. And that is what we derive on this board. Okay. But yeah, in some sense, like this board of equations is the answer to why. Okay, but there's like this asymmetry, right? Where on the one hand, if you're not calibrated with respect to H, on the one hand, if you can decrease error with H, you're not calibrated with respect to H. But on the other hand, if you're not calibrated with respect to H, there's this like H prime you can use to decrease error with. H prime is some other function that is not necessarily in your class big H. Okay. So I want to get rid of that asymmetry by assuming it away. But it's going to be a natural assumption. So I'm going to restrict attention to classes of functions that are closed under affine transformations. Okay. So we'll say that H closed under affine transformations if for every pair of real numbers A and B, the function H prime of X, which is just A times H of X plus B, is also in the class. Okay, so it's saying I can take affine transformations of my functions and not step outside of the class. Okay, so Okay, so first of all, lots of things are closed under affine transformations. For example, the set of linear functions. So if you think that you're interested in, if you think you're really good at solving linear regression problems, and so you want to take H to be linear functions, you're good. If you want to take the set of degree D polynomials for any D, it's also closed under affine transformation. So you could do polynomial regression, you're good. If you want to take neural networks with sort of the right structure, you're okay. If you want to take regression trees where what you're going to do is just go down, some series of tests to a leaf node that just is parameterized by a real number, you're good. Okay, so life is going to be a lot more convenient if H is closed under affine transformations, but for natural classes of regression functions, this is not a severe restriction. Okay. And what I want to note is that if H is closed under affine transformations, then these two lemmas we proved are sort of symmetrized. Right? On the one hand, we know that if there's any H in your class that can improve on squared error for your current prediction on one of the level sets, then there's another function in your class on which you're miscalibrated. And similarly, if there's any function in your class on which you're miscalibrated, there's some H in your class on which you can improve significantly in squared error. These aren't necessarily the same function, but they're both in your class if H is closed under affine transformation, because the function H prime we use in this lemma is just an affine transformation of H. Okay, so that means that if we're talking about classes that are closed under affine transformation, I can view these two conditions as equivalent. I'm not calibrated on H, and I can improve by at least a little bit on one of my level sets using some function in H. Make sense? Okay. So eventually, I want to get to the statement that's sort of going to characterize exactly when multi-calibration with respect to H implies Bayes optimality. But before we do that, we need to think about how we are even going to get multi-calibration with respect to H, because we've seen algorithms for multi-calibration before for groups, but they don't exactly apply here. First of all, our definition is more general. And second of all, there was like this algorithmic step that seemingly required enumerating over all of the groups, and there's definitely continuously many of them if my set is closed under affine transformation. So we're going to need a better way of accessing this class than like enumeration. And so what I'm going to assume about this class is that I can solve squared error regression problems over it. Okay, so I'm going to assume in constructing an algorithm that I have a subroutine, which I'll call for obscure computer science reasons an oracle, but it's just a subroutine that takes as input like a distribution on points or a sample of points, and just outputs the little h in the class that minimizes squared error. Okay, so like linear regression is this subroutine for the set of linear functions. Polynomial regression is the subroutine for the class of, degree D polynomials. And more generally, the algorithm that implements regression over this class is your subroutine. Okay, so let's say that A sub H, an algorithm, is an oracle for squared error regression over H if, for every distribution, if I run this little subroutine on the distribution, if you want to think of the distribution, you can think of, if you want, as the empirical distribution over a sample. So it makes sense to feed it to a learning algorithm. This thing outputs some function, little h, that solves the squared error minimization problem, okay, such that little h is the minimizer of the expected squared error under this distribution D of h prime of x minus y squared. Okay, so it's a regression oracle. It's just a regression algorithm. Okay, so like, again, if h is the set of linear functions, the solution to this thing has a closed form. It's like a super easy algorithm. Similarly for polynomial regression. For any convex regression problem, this is just a convex optimization problem. And more generally, even if the sort of algorithmic problem of optimizing this isn't especially well behaved, oftentimes we have, you know, good algorithms that solve this problem, even if we can't, even if we don't have provable guarantees, right? So we can do regression with deep neural networks with gradient descent. It's not convex, but due to magic, it works anyway. Okay, and so the premise in sort of the algorithm design exercise I'm going to go through now is I'm just going to assume that we have an algorithm that can solve this problem over H. And then I'm going to try to design an algorithm that is efficient otherwise, just makes calls to this learning oracle, this sort of regression oracle over H. And I want it to output an algorithm that's multi-calibrated with respect to H. Okay, and that means that if you really can implement this algorithm, this learning oracle in sort of some provably efficient way, like if you're in any convex regression problem, like linear regression or polynomial regression, then the algorithm we're going to give is like provably efficient as well. And more generally, if you want to try to do this with some function that is not provably learnable, you know, the algorithm we're going to give lets you multi-calibrate whenever you can solve this problem. So that you might call these oracle efficient algorithms, or just algorithms that reduce the problem of multi-calibration to the problem of regular old regression. Okay, so let's call this regression multi-calibrate. And as usual, you know, you can start this, you can start from scratch, or you can think of this as a post-processing routine. So you can start with some initial model F that you'd like to improve. We're going to ask for approximate multi-calibration. So the algorithm needs to know how approximate you want it to be. We used to feed in like an explicit collection of groups as an argument to this thing. Now the thing we're going to feed in is a regression oracle for some class H. We're going to access H only through this regression oracle. We need some distribution over which to multi-calibrate. And there's going to be a bound B that will come into the theorem and is related to this observation that for real valued functions, especially those closed under affine transformation, it doesn't make sense to sort of uniformly speak of approximate multi-calibration, because I could just multiply H by like 10 zillion and make the multi-calibration worse by a factor of 10 zillion. We have to talk about multi-calibration at some scale where B somehow bounds the scale of the functions H. And so that's what this B is. Okay. And the algorithm will sort of look kind of familiar, except we're going to use this regression oracle. So there'll be some discretization parameter, which as usual we call M, and we will set this to be 2B over alpha. And we'll set f0, where f0 might be, or f might be some arbitrary like real valued function, our algorithm is going to operate over functions that have sort of discrete range that are multiples of 1 over m, as we often do in this class. And so our first move is just going to be to round the function f to multiples of 1 over m. Just remember what this notation does. We've used it in our previous multi-calibration algorithms, but it just takes any point or the output of a function and maps it to the closest multiple of 1 over m in the unit interval. So 0, 1 over m, 2 over m, up through 1. Okay. And it's going to be an iterative algorithm. It's updating. We're going to have an f1 and an f2 and an f3. And the thing we're going to keep track of is the expected squared error of these models. And so let's say that at round 0, we'll just start off. The thing we'll call error 0 is the expected squared error of f0. And just as a bookkeeping trick, let's say that the error at round -1 is minus infinity. And we'll keep track of what round we're at with this counter t, and initially it's 0. We start at round 0. Okay. So what are we going to do? We're going to keep updating our model. And each time we update the model, it'll decrease the squared error by a little bit. And we're going to keep track of how much it decreased the squared error by. And we want to keep going so long as we're making substantial progress. The stopping condition will be when the last round's update only decreased the squared error by a little bit. So we'll keep going while the difference between the error yesterday, error t-1, and the error today, so this is the decrease in error from round yesterday to round today, we'll keep going while that decrease was at least alpha over 2b. Okay, and the whole purpose of this accounting trick of saying the error of -1 was infinity was just that we're going to run this loop at least one time. Okay, so like at round 1, that's true. Okay, so what are we going to do? We're going to look at the level sets of our predictor. There's m+1 of those. And we're going to run our regression oracle on each of those level sets. So for each level set of our predictor, right, the fact that we're rounding to the nearest multiple of m means the range of our predictor is this discrete grid, 0, 1 over m, 2 over m, up through 1. We will look at the level set v of the predictor. That is just the distribution that we will call dv t+1. It's just the conditional distribution, conditional on the event that our current round predictor equals v. Yeah. Oh, that's a pretty good point. Yeah. Because I want to look like we've decreased the error. Yeah, so this probably should start out as plus infinity. Good point. Otherwise, the algorithm would halt at round 0. Okay. Okay, so we're going to look at the conditional distribution on each of the level sets of the predictor. And what are we going to do? Well, we really only have one move. Like someone gave us a regression algorithm, we're going to use it. So we will run the regression algorithm on this level set. It'll solve the squared error regression problem on that level set, and it'll give us back a regression. It'll give us back some function that I'll call HV for round t+1. This is the thing that minimizes squared error on yesterday's, on the level set, on one of the level sets V of yesterday's predictor. And I'm going to come up with a new predictor that is doing the thing that you sort of obviously want to do, right? What have I done? On every level set of my current predictor, I've solved the squared error regression problem. Now, I'm doing as well as the best predictor H prime in my class. H prime is closed under affine transformation. So in particular, it includes constant functions. And my current model, when I restrict attention to a level set, by definition is a constant function. That's right. So I can't, this regression oracle won't cause me to do any worse than my current model. My current model is just predicting a constant. This has the capacity to also predict the best constant, but it might do better. Okay, so the thing I want to do is on each of the level sets, I want to sort of swap out what I was previously doing on that level set, which was just predicting constant v. Instead, I want to predict according to this new model I just learned. I'll do that for all of the level sets. Okay, so a concise way to write that is I will just let this new function that I'll call f tilde t plus 1 be the sum over all of the level sets of the indicator that yesterday's model would have predicted something in this level set times the model that I just learned for this level set. Right, and this is just saying swap out all of the level sets, because for any particular x, at most exactly one of these indicators will be 1. It'll fall into exactly one of the level sets, and so I will use the prediction that I just learned on that level set. Okay, so this is just some concise way of writing swap out all of the predictions on each level set for these new models I just learned. This thing might be real valued again, so I need to round it. So let's let f without the tilde, t plus 1, be what I get from rounding this function to the nearest multiple of 1 over m. And that's it. And then if we break out of this loop, I'll just output not the final model, but the model from one iteration ago. Okay. Does the algorithm make sense? So like, is it clear what the algorithm is doing? It's pretty simple, actually. It's just saying, we're going to repeatedly do this like simple operation. I've got this current predictor. It's got these level sets. For each of the level sets, I'm going to see if I could do a little bit better on that level set by using the best function in my class H. How do I do that? I just cut the data up, to partition it according to level sets. And on each of the level sets, I run the regression algorithm, which gives me the best function in H. And then I swap out the level sets for this thing that I learned that can only be better. And I keep doing that until the decrease, each time that the error will only go down. But I'm going to, if the error starts going down by, just like super low order bits or something, I'm going to stop. I'm going to stop doing it when the error hasn't decreased substantially. Okay, so while I'm making rapid progress, I keep going. But if I stop making rapid progress, I say good enough. Okay. And so what can we prove about this?
Constant before the last step.
Yeah.
We learned a constant element is true, correct?
Yeah, seems kind of dumb, right? Maybe you don't need to. So that's like a homework problem. Okay, so one thing. What is the objective here? If the objective is to minimize squared error, then for sure this was super dumb. Because ft, we stopped because ft had error that was only a little bit smaller than ft minus 1, but it was a little bit smaller, so why not just use that? So if the function was, if the goal here was minimize squared error, which is one of the goals, then yes, you should just output ft. If the goal is to be multi-calibrated with respect to h, probably you could do that too, but the argument is going to be a little bit easier if we output this. Because what we're going to say is that if you are appropriately multi-calibrated with respect to H, then this iteration won't decrease the error very much, and you'll break out of it. The problem with outputting the last thing is then we'd have to think about what would happen at the next iteration. We haven't tried the next iteration yet. Now, probably it's okay, but this saves a step of the argument and doesn't get a bound that's any worse. Good question, though. Maybe as a homework problem, you can figure out if the theorem that we're about to prove with respect to the multi-calibration properties of this algorithm is still true if I output ft instead of ft minus 1. Other questions? Okay. So what's the theorem? Fix any distribution, any model, any approximation term alpha, and any class of loss functions H that are closed under affine transformation. Okay, so anything can be arbitrary except, I'm going to assume that H, this class of functions that you want multi-calibration with respect to, is closed under affine transformation. Okay, and we've got, by assumption, of course, a regression oracle for H, a squared error regression oracle for H. Let's let HB denote the set of functions in H such that H of x squared is at most B. Okay, so remember it's closed under affine transformation. So if H is in here, so is a million times H, but HB is not closed under affine transformation. HB is the set of functions in H that satisfy some bound. Okay. So this algorithm, which you give it an alpha and a B, this algorithm regression multi-calibrate halts after a number of rounds that is at most 2b over alpha. And outputs this function ft minus 1 that is alpha approximately multi-calibrated on the distribution D with respect to the class of functions HB. Okay, so you get multi-calibration with respect to some bounded norm. And of course, like if you're alpha approximately multi-calibrated with respect to HB, you're 2 alpha approximately multi-calibrated with respect to H2B. It's not really a hard cutoff at B. This is just like a scaling factor. Is the theorem clear? Oh, and just note, so this thing halts after at most 2b over alpha many iterations. At each iteration, it has to run m, it makes m calls to a regression oracle, one for each level set. M is also 2 beta over alpha. So in all, this algorithm solves 2 beta squared or 4 beta squared over alpha squared many regression problems. Okay, so algorithmically, this is a reduction from the problem of regression, which we assume we can solve, like regular old regression, to the problem of multi-calibration, where to get alpha multi-calibration with respect to functions bounded with sort of norm bounded by b, we have to run the regression oracle at most, beta squared over alpha squared many times. So, not infinitely many times. Okay, let me prove this theorem. Then I'll release you on some kind of break where you can do what you will. Then we'll come back, and thus far we will have proven a theorem only about how this algorithm results in multi-calibration, but we'll want to think about when we can extend that to a theorem that says that this algorithm promises not just multi-calibration, but accuracy. Okay, we want to characterize when that's the case. Okay. So the first part of the theorem is like immediate. It's like the halting condition. The claim is this halts after at most 2b over alpha many iterations. Can anyone just like looking at the algorithm tell me why that is?
Like 1 over n improvements, and the error at most 1. So
Yeah, so like, the initial model, the labels we're always assuming are bounded between 0 and 1. The initial model outputs predictions between 0 and 1. So like the squared error of the initial model is at most 1. And squared errors, because they are squares of numbers, can't go below 0. Okay, so at any moment, the squared error is like a number that starts at 1 and can't go below 0. And the stopping condition is that the error has gone down by at least alpha over 2 beta. So if we haven't stopped, then every round the error has gone down by at least alpha over 2 beta. And starting at 1, how many times can you go down by alpha over 2 beta before you get like, negative, which would be a contradiction to the properties of squares, at most 2 beta over alpha many times. Okay, so in this case, the stopping condition is actually like baked into the algorithm. That's like obvious. It like stops after 2 beta over alpha many iterations, like by definition, basically, of the halting condition on the loop. So the only thing to show is that when it stops, we actually have something that's approximately multi-calibrated. Okay. So so what we want to show is that the model it outputs is approximately multi-calibrated. Okay. So suppose not. I suppose it's not alpha approximately multi-calibrated with respect to these functions that have magnitude bounded by b. What we'll show is that in that case, if I look at the decrease in error between round t minus 1 and round t, this is actually pretty big. It's bigger than alpha over 2b. And that's going to be a contradiction, because if we stopped at this round, it was because the decrease in error was less than alpha over 2b. Okay, so Well, the only thing we need to show is that if we're not alpha approximately multi-calibrated for functions that have a bound of b, then at the next round, we're going to decrease the error by at least alpha over 2b, and that'll be a contradiction, and so we'll be done. Okay. So what does it mean that we're not approximately multi-calibrated? Let's just remember the definition of multi-calibration. We know that there must exist some h in this set HB, right? Some function h such that we're supposed to be multi-calibrated with respect to it. But if I look at my squared calibration error, which is just sum over all of the level sets, the probability of falling into that level set times the expected value of h of x times y minus v, given that I do fall into that level set, squared, right? This thing was supposed to be less than alpha, but like we're assuming like we weren't alpha multi-calibrated. So in fact, this thing must be bigger than alpha. Okay. This is the sum over a bunch of terms. Let me just give a name to each of the terms. There's one for each level set. Let me call that alpha v. Okay, so we have these quantities alpha v such that, you know, the sum over all v of alpha v is greater than alpha. That's just this statement here. Okay. So remember, we have this lemma connecting failure to be multi-calibrated with the ability to decrease squared error on a level set in both directions. Okay, so let's just apply that lemma. We're assuming here that we have failed to be multi-calibrated, which means that like we must have failed to be multi-calibrated, you know, on a substantial amount on some substantial fraction of these level sets. So I want to argue that there must be some function in H that could decrease the error on that level set by a substantial amount. Our algorithm, since it called this regression oracle, will have found it, and therefore we will have decreased the overall error by a substantial amount. That's the form of the argument. Okay. So what do we know? We know that for each v, there exists some function hv in H such that if I look at the difference in squared error between ft minus 1 and hv, on this level set, so this is at least, well, the miscalibration error on this level set, which is this thing, was at least alpha v over the probability of lying in the level set. Okay. And if you recall our lemma, the decrease in squared error is going to be the miscalibration error on the level set. So that's alpha v over the expected value of h of x squared on the level set. Wait, no, sorry, alpha v over the probability of landing in the level set. Alpha v over the probability of landing in the level set. And then we did have this normalization term. The decrease depended on the norm of h, right? So the decrease wasn't quite as good as this. It was multiplied by 1 over the expected value of h of x squared on the level set. Okay. But this is at least alpha v over the probability of landing in the level set times 1 over b. Because h wasn't arbitrary, h was a function whose squared norm was at most b. Okay. So this is saying that on every one of these level sets, v, we can, by swapping out the level set by the thing that we learned with our regression oracle, we decreased the error on that level set by some amount that was equal to sort of alpha v over the probability mass of the level set times 1 over b, where these alpha v's, we know that they, if I don't know what any particular one of them is, but I know if I sum up all of them, I get at least alpha. Okay. So this rounding operation is annoying. So let's first pretend we didn't do it. Right, so let's first just look at what is the expected decrease in squared error when I go from f of t minus 1 to ft twiddle. Okay, so ft twiddle is just sort of what I do after the level set update, but before I round. Okay, how much did I decrease the squared error by doing this? Well, by linearity of expectation, I can break this up by looking at the squared error on each of the level sets. Okay, so this is just the sum over all of the level sets of the probability. These are the level sets of ft minus 1 of the probability that I land in that level set times the expected decrease in squared error on that level set. Now, I'm looking at this function f twiddle on the level sets of ft minus 1. And I know exactly what that is because f twiddle on each level set v of ft minus 1 is just exactly equal to hv, right? Like this thing that I learned, right? So the level sets of ft minus 1 are exactly the things that define what f twiddle does, f twiddle t. Okay, so this is just sum over all of the level sets of the probability of landing in that level set. The expected decrease in error when I compare ft minus 1 to this function hv t minus 1. because f twiddle is just the function that I get when I swap out every level set v of yesterday's predictor with this function hv that I just learned with my regression oracle. No, I don't think so. +1. Oh, let's see. F twiddle t plus 1 is defined in terms of hv t plus 1. So the index on, oh, you're right. Good point. Yeah, okay, good. So the index on the H is the same as the index on the F. Okay, good. Okay. Now this HVT is not necessarily the same as this HV that we learned over here, right? Like this HV was derived with respect to some function H we were not multi-calibrated with respect to. This HVT was derived by solving a squared error regression problem. No reason to think they're the same thing. But this HVT is the thing that minimizes squared error on the level set, and so has only smaller squared error than this one. Right? So this is at least what I get if, again, I take the expectation over the level sets. Of the expected decrease in squared error, error ft minus 1 with this function hv that whose existence we established over here. Okay. And here we're just using the fact that like hv is some function and hvt is the function that minimizes squared error. So that one only has larger squared error. Okay. But this we understand. We just bounded this thing, right? Like this decrease in squared error is just alpha v over the probability of the level set times 1 over b. Well, conveniently, we're also multiplying by the probability of the level set. So this probability of the level set cancels out. And this is just the sum over all of the level sets of alpha v over b. And remember, the sum of all of the alphas is, the sum of all the alpha v is at least alpha. It's bigger than alpha. So this is bigger than alpha over b. Okay. Now we wanted to show that the decrease in error was bigger than alpha over 2b. It seems we've outdone ourselves. We've shown it's bigger than alpha over b, but not so fast. This was the decrease in error when we compared ft minus 1 to f twiddle t. Okay, the error is going to get a little bit worse when we round f twiddle t. Okay, so how much worse? Well, it'll get worse by at most 1 over m, because we're rounding to the nearest multiple of 1 over m. What is 1 over m? Well, 1 over m is nothing more than alpha over 2b. Okay, so we decrease the error by alpha over b if we were updating to f twiddle. Then by rounding, we potentially increased it by alpha over 2b. And so all in all, we decreased the error by more than alpha over 2b. And therefore, if we weren't multi-calibrated, by the time we got to ft minus 1, we would not have halted, because we wouldn't have satisfied the halting condition. And since we did halt, we were multi-calibrated. Okay. So we gave an algorithm, very simple algorithm, that only solves squared error regression problems and quickly converges to a multi-calibrated regressor. So for example, if you wanted to be multi-calibrated with respect to the set of linear functions, this would just be at every round solving a linear regression problem, which we have in closed form. Okay. Let's take a 10-minute break, come back at 3:31, And we will talk about how this algorithm not only gives you multi-calibration, but under certain conditions actually gives you the Bayes optimal predictor. Like you might have started with like linear regression and you ended up with something like way better. Okay, I'll see you in 10 minutes. 3:31. All right. So let's carry on. So we've got this algorithm, and it seems like it's probably, feels like, a good idea if what you want to do is decrease error, because like that's explicitly what it's doing now. Like before, when we had these multi-calibration algorithms that were like shifting things around, the thing they were most explicitly doing was just fixing problems with multi-calibration. And we kind of had to like prove in the analysis that actually they weren't making things worse with squared error. That was what we proved, that like squared error was a potential function. Here, the algorithm is sort of flipped around. Like the algorithm is explicitly trying to minimize squared error. And we prove in the analysis that like along the way, it has to end up with multi-calibration. But when you look at an algorithm like this that's clearly trying to minimize squared error, the question is, how low can you go? Like how accurate can we expect an algorithm like this to model some data distribution? And in particular, like when can we expect an algorithm like this to find the Bayes optimal classifier? Okay. Now, finding the Bayes optimal classifier seems like a lot to ask. Like Bayes optimality is very strong. So we'd like to sort of, to understand that, we would like to reduce it to our ability to solve what seems like a much weaker kind of learning problem, where we ask much less. Okay, so we're going to take a statement that I will describe as a weak learning statement or a weak learning assumption, the assumption that our regression oracle, our regression algorithm over H can, do a little bit, can make predictions that are like a little non-trivial. And I want to show that, okay, if we take that assumption seriously, then this algorithm will lift that assumption to imply that we get Bayes optimality. So we can think of this as what's called a boosting algorithm. It takes a learner that satisfies a weak guarantee and turns it into a learner that satisfies a much stronger guarantee. In fact, it's not a coincidence that this same algorithm, which we just proved is a multi-calibration algorithm, is also a boosting algorithm. We are going to give a tight if and only if characterization that says, if our class H satisfies property blah, where blah is something I will tell you in a moment, then multi-calibration with respect to H implies Bayes optimality. And similarly, if multi-calibration with respect to H implies Bayes optimality, then H must satisfy property blah. So if you want to know whether being multi-calibrated with respect to H implies Bayes optimality, it is equivalent to knowing whether blah is true. Okay. Okay, so what is blah? Okay, so let's fix the distribution D and the class of functions H. And let's let f star of x just be the Bayes optimal predictor with respect to squared error, which you recall is just the expectation of y given x. Okay, so if I want to minimize squared error over the set of all functions over this distribution D, I can't possibly do better than f star. F star is like the target. That's Bayes optimal. So let's say that H satisfies the weak learning condition with respect to this distribution D, if for every subset of the feature space that has, non-zero measure, that, and there's going to be a conditional here, if the squared error of the Bayes optimal predictor on this subset of the feature space is better than the squared error of a constant prediction, the best constant prediction. So far we've said, if you zoom in on some like part of the distribution, on some subset of the feature space, it might be that, like the conditional label expectation is constant on this subset of the feature space. You might have zoomed in on like a level set of the Bayes optimal predictor. But if you didn't, if the Bayes optimal predictor predicts a little bit better than a constant function, then if H satisfies the weak learning condition, there exists some H in H that also does a little bit better than a constant prediction. Okay. Such that the squared error of H on this subset of the feature space is also better than a constant predictor. Okay, so let's think about this for a moment and think about why we are justified in calling it like a weak learning assumption. So the Bayes optimal predictor might do much better than a constant function. The Bayes optimal predictor could have 0 squared error on this level set for all we know. All we are requiring of the weak learner is that it do a little bit better than a constant prediction. Infinitesimally better is good enough. Okay, so great. Like it could be that the Bayes it could be that like the labeling is deterministic. It could be that like the Bayes optimal predictor has 0 error. Okay, if it has 0 error, it also has 0 error on every subset of the feature space. All we would be requiring in that case is that on every subset of the feature space, the weak learner can have error that is like a tiny bit better than trivial. Right? For a squared error prediction problem, it's trivial to do as well as the best constant. You just predict the label mean. We're just saying the weak learner should do like a tiny bit better than trivial whenever that is possible. It's not possible on level sets of the Bayes optimal predictor, and so we're not going to require it there. We're just saying whenever we're not on a level set of the Bayes optimal predictor, and so Bayes optimal is better than a constant prediction, that the weak learner should be able to, just do like a little bit better than just reporting the constant function, which is the label mean. Okay, so is the assumption clear? Like when you write it this way, you might be tempted to think, we're asking something super strong. You have to, like, if the Bayes optimal learner does something, we have to do it too. But that's not what we're asking. We're saying we want to predict better than a constant function whenever doing so is possible. But we don't care how much better. The Bayes optimal predictor could be perfect. It could be like leaps and bounds better than a constant predictor. This just asks that we do infinitesimally better than a constant predictor. Does that make sense? Okay. So that's the weak learning condition. Let's also say what it means for multi-calibration to imply Bayes optimality. It means what it sounds like, but let me write it down. fix a distribution D and a class of functions H. Multi-calibration. With respect to D and H implies Bayes optimality if for every function f that is multi-calibrated with respect to D and H is Bayes optimal. So in particular, it had better be that the expected squared error of f is equal to the expected squared error of f star. Okay, so it's not just saying that like the Bayes optimal predictor is multi-calibrated. The Bayes optimal predictor is by definition multi-calibrated with respect to any class of functions H. It's saying that every function that is multi-calibrated with respect to H is Bayes optimal, right? That's what the implication means. So if the only thing I tell you is that you're multi-calibrated with respect to H, then you can also conclude without knowing anything else that you're Bayes optimal. Okay, so this is the weak learning condition. This is what it means for multi-calibration with respect to H to imply Bayes optimality. This is an algorithm that gets multi-calibration with respect to H. Okay. And then here's the theorem. Let's fix a distribution D and a class of functions H that is closed under affine transformations. Okay. Then the statement that multi-calibration with respect to distribution D and class of functions H implies Bayes optimality. Is true if and only if H satisfies the weak learning condition with respect to D. Okay, so is that clear? We've got these two things. H could satisfy the weak learning condition with respect to D. That just means that H can predict better than sort of a trivial constant predictor on any subset of the data domain whenever doing so is possible, whenever the Bayes optimal predictor does so. Whenever that is true, whenever H satisfies the weak learning condition, then multi-calibration with respect to H will imply Bayes optimality. Okay, in particular, like this algorithm will converge to a Bayes optimal predictor. And also, we haven't assumed too much in doing this, in that if I have some class H such that multi-calibration with respect to H implies Bayes optimality, well, it's got to be that H satisfies the weak learning condition. This is an if and only if characterization. Multi-calibration implies Bayes optimality exactly when it satisfies this weak learning condition. Okay.
Wait a second. So whenever there's a possibility to improve, this algorithm gets me to because that's what the weak learning condition.
The weak learning condition, yes.
Whenever there's a possibility to improve, then that algorithm is enough for me to improve with respect to it.
Yes, that's right. So the one direction, pretty intuitive, is what's this algorithm doing on every level set, which is a constant, it's a subset of the feature space on which we're currently predicting a constant. This is saying, let me find the best thing in H. And the weak learning condition is saying, well, either you're going to find an improvement, or if you don't find an improvement, you're already Bayes optimal on that level set. Okay, so if you satisfy this condition, it's sort of immediate that this algorithm makes progress at every iteration. And then it turns out the reverse is also true. If this algorithm does not make progress at every iteration, even when you're not yet Bayes optimal, like if it stops, before you're Bayes optimal, it's got to be that what we've done is we've found a level set on which it's therefore a subset of the feature domain on which it's possible to do better. The Bayes optimal predictor does better. You're not Bayes optimal, but nothing in H can.
So sometimes finding the Bayes optimal predictor is not easy because there's problem. Well, in this case, it's giving me like a mindless way of just reaching it.
If you satisfy the weak learning condition.
Satisfying the weak learning condition is just saying that it's improvable through Bayes optimal.
That's right. Yeah. So, in some sense, you run this algorithm, it'll converge to the Bayes optimal thing, or if it doesn't, it's a proof that you didn't satisfy your Bayes hypothesis class didn't satisfy the yeah. Okay, so is the statement clear? Okay. So there's two directions to show. So first, the first thing we want to show is that if we satisfy the weak learning condition, if H satisfies the weak learning condition, then any function that is multi-calibrated with respect to H had better be Bayes optimal. Okay. And so suppose otherwise. Okay. First, direction one, we'll assume that H satisfies weak learning. And we'll suppose that F is multi-calibrated with respect to H. But for point of contradiction, we will imagine that F is not Bayes optimal. And our goal is to derive a contradiction to argue that this actually, the state of affairs cannot occur. Okay, so suppose H satisfies the weak learning condition and F is perfectly multi-calibrated with respect to H, but actually, if I look at the squared error of F, this is strictly larger than the squared error of F star. Okay, failure of Bayes optimality. So again, by linearity of expectation, we can sort of divide up this expectation level set by level set. Okay, so equivalently, if I look at the expectation over the level sets, so the sum over all of the level sets, range of F of the probability of falling into that level set times the expectation of the difference between the squared error of f and the squared error of f star on this level set this is bigger than 0. This is what failure to be Bayes optimal means. Okay. So, just to make things simple, although this isn't strictly necessary, let's assume that whatever the range of f is, it's like countable, merely countably infinite. Like the thing I want to avoid is that the level sets all have measure 0. Okay, so let's say the range of f is merely countably infinite, which if you've implemented f on like a computer is a pretty mild assumption. Okay, so like, this is like the sum of a bunch of non-negative terms, and it's non-negative, so one of them's got to be, a sum of a bunch of non-negative terms that is strictly positive. They're all non-negative because you can never have squared error better than the Bayes optimal predictor. And so one of them has to be strictly positive. Okay. So in particular, there must exist some level set such that, the level set has positive probability. And on this level set, our predictor has higher error than the Bayes optimal predictor on this level set. Okay. Now, let's just call the set of all points in our data universe such that our predictor predicts this constant v. Let's call that S. Okay. Now I want to invoke our sort of weak learning hypothesis. So on a level set of our predictor, we are predicting a constant function. In fact, we've assumed that f is multi-calibrated, which means in particular it is calibrated. So we're not just predicting a constant on this level set, we're predicting the best constant. We're predicting the mean of the labels on this level set. And the Bayes optimal predictor is doing better. So that means that on this level set, it's possible to predict better than a constant. We don't know how much better, but it's possible to predict a little bit better than a constant. And so in particular, like the weak learning assumption means that there's some function in H that predicts better than a constant on this level set. Okay. So in particular, weak learning assumption implies that there must exist some hypothesis H that when we look at its squared error, level set it is strictly better than the squared error of our predictor on this level set, which was just predicting a constant. So we're looking at a level set, and the weak learning assumption is that whenever it's possible to predict better than a constant, which it is because we weren't Bayes optimal on this level set, there's something in H that predicts better than a constant. Okay, there must be some H in our hypothesis class H that predicts better than we do on this level set. But now we invoke our lemma that relates multi-calibration to the ability to decrease in squared error, right? So, right, like, we have this equivalence. So there exists some H prime in H such that if we look on this level set at the expectation of H prime of X times Y minus V, given that f of X is V, that this is positive. And this level set has positive probability, and so this certifies that we are not multi-calibrated on H. Right? This is a violation of multi-calibration. Okay, so what have we done? We've established one direction of this equivalence. Right? We've said if H satisfies the weak learning condition, then multi-calibration with respect to H must imply Bayes optimality, because we started with the presumption that we have a function that is multi-calibrated with respect to H, but not Bayes optimal, and we derived a contradiction. Okay, so if H satisfies the weak learning condition and you multi-calibrate with respect to H, then the only way you could have done so is by actually learning the Bayes optimal predictor. In particular, like running this algorithm will converge to Bayes optimality. Okay, so now the other direction, like, have we made too strong an assumption to get this conclusion? So we want to show that if we've got some H such that multi-calibration with respect to H implies Bayes optimality, then it's got to be that H satisfies the weak learning condition. That'll prove that we haven't assumed too much, and we've actually identified the correct condition. Okay, so in the reverse direction, we want to say if H not satisfy weak learning condition, then multi-calibration with respect to H does not imply Bayes optimality. Okay. In particular, what we're going to do is we're going to construct a particular function f such that f is not Bayes optimal. Okay, so we want to construct f that has two properties. First, it should be that f is not Bayes optimal. So we want that the expectation of f of x minus y squared is bigger than the expectation of f star of x minus y squared. But secondly, so that f is in fact multi-calibrated with respect to h. Okay, that'll prove what we want. It'll say, look, if you don't satisfy the weak learning condition, then I can, by like looking at h, and in particular, the way in which you fail to satisfy the weak learning condition, I can construct a function f that is perfectly multi-calibrated with respect to h, but not Bayes optimal. Okay, so if we want multi-calibration with respect to h to imply Bayes optimality, since we have the ability to construct functions like this, it had better be that h satisfies the weak learning condition. Okay. Okay. So what does it mean that h does not satisfy the weak learning condition? Right. So we know if h does not satisfy the weak learning condition, that there exists a subset of the feature space that has non-trivial mass, that has positive measure, such that on the one hand, the Bayes optimal predictor restricted to this subset of the space does better than a constant. But such that for every function little h in my class, poor little h does not predict better than a constant. The prediction, the squared error of little h subset is no better than the squared error of the best constant on this subset. Okay, so this is just the opposite of the weak learning condition. The weak learning condition says if it's possible to predict better than a constant, then there's something in h that can. If you fail to satisfy the weak learning condition, there's some region of feature space such that on this region, it is possible to predict better than a constant, but nothing in h can do it. This is just what it means to not satisfy the weak learning condition. Okay, so in particular, like there's some particular set S like this, and I'm going to define f, my like calibrated, multi-calibrated, but poorly predictive function as a function of S. Okay. So let's let P of S denote the best constant prediction on this set S. Right? What is the best constant prediction on this set S? Well, we're minimizing squared error. So it's just the expected value of the label on this region of the distribution. That's the best constant you could predict on this set S to minimize squared error. Okay, and let's define our function f of x as follows. Our function f of x will actually be Bayes optimal. It'll output f star of x whenever we're not in this region of feature space S. So for any x not in S, it'll just output the Bayes optimal prediction, the conditional label expectation. But it'll just output this constant prediction, C of S, if x is in S. Okay, so it's like a Bayes optimal predictor, except on this like region S where for whatever reason, it can't predict better than a constant. It just predicts the best constant there. Okay. And we want to argue, on the one hand, that F is not phase optimal. And on the other hand, that F is multi-calibrated with respect to H. Now, it's kind of obvious, actually, that F is not phase optimal from the way we constructed it, right? Like, what's the squared error of F? Well, it's, like the probability that we're in set S of the squared error of the best constant predictor in S, plus the probability that we're not in S of the squared error of the base optimal predictor when we're not in S. And of course, conditioned on not being in S, the squared error is optimal by construction, but conditioned on being in S, our squared error is the squared error of the best constant predictor. And by hypothesis, the Bayes optimal predictor does better than that. So by construction, this is not Bayes optimal because it's possible to do better than a constant prediction on S, but F is making a constant prediction on S. Okay. So, like by inspection or 2 lines of algebra, F is not Bayes optimal. But what we want to do is we want to show that it is multi-calibrated with respect to H. Okay. So, okay. So again, we'll prove this by contradiction. So suppose F is not multi-calibrated with respect to H. What does that mean? Well, that means there exists some H, some little h, and some level set of our predictor such that if I look at the expectation of h of x times y minus v, conditional on the event that our predictor predicts v, that this is, well, in absolute value, it's not 0. It's either bigger than 0 or less than 0. But since I've assumed that h is closed under affine transformation, I might as well assume it's bigger than 0. Because if it's less than 0, I'll take negative h, which is also in our class. Okay. This is what it means to not satisfy multi-calibration. And from this, I want to derive a contradiction. Okay. So I want to again apply our lemma connecting failure to satisfy multi-calibration with the ability to sort of decrease the error on a level set. Okay, so we know from the lemma we proved at the beginning of class, there exists some function h prime, also in H, such that the expectation of the squared error of h prime on this level set is smaller than the error of f on this level set. Okay, so if there's a failure of calibration, it must be that there's some level set such that we can do a little bit better on that level set using h prime. Okay. Now I first claim that it had, this just says there's some level set, but like I first claim we know what level set that is. It's got to be that the level set on which it's possible to improve on f had better be the level set that predicts C of S. Can anyone tell me why? Yeah, like on every other level set, we predict f star of x, we're Bayes optimal. So it is not possible to improve on squared error with any function on any level set other than C of S. Okay, like if V was not C of S, this would already directly be a contradiction because we would have something that had lower squared error than the Bayes optimal predictor, and you can't. Like that's the definition of Bayes optimality. Okay, so we know that this level set on which H can improve is the level set that predicts C of S. Okay. So that's progress. So let's look at the squared error on this level set. Right, the squared error of H prime of X on this level set, conditional on f of X equaling C of S. Once again, we can sort of partition this and compute the squared error on two parts of the partition. Not everything in this level set is necessarily in S, right? Like everything in S is in this level set, but like there might also be points for which C of S is actually what the Bayes optimal predictor predicts. And so we might on this level set, have points in S and also points not in S. So I want to divide my attention and think about what is the squared error on S and what is the squared error not on S. Okay, so I can write my squared error as the weighted combination of the squared error in the two parts, right? It's the probability that the point is in this set S times the squared error of H prime conditioned on the point being in this set S plus the probability that the point is not in the set S, but that still our predictor predicts C of S. And we still have to be in the level set of the squared error of the predictor conditioned on not being in the level set and or not being in the set S and our predictor predicting C of S. Okay. Now, this is at least, again, thinking about these two terms separately. The probability that we land in this set S times the squared error of our predictor conditional on landing in this set S plus probability that we don't land in this set S even though we're in the level set, the same level set as the set S, times the expected squared error of our own predictor given that we don't land in the set S, even though we land in the same level set. Okay, and this is because our predictor by definition is Bayes optimal anywhere, anywhere that's not in S. So conditioned on not being in S, you can't beat us on squared error. And so, at best, you match us in squared error. And so, but like nevertheless, right, like the claim is on this level set, you have lower squared error than we do. You can't have lower squared error than we do when you're not in S. So the only way this can occur is if you have lower squared error than we do when you are in S. Okay, so an implication of this is that it's got to be that the squared error of H prime given that we're in the set S is strictly smaller than the squared error of a constant predictor on the set S. In particular, our predictor on the set S just predicts this constant C of S. Okay, C of S is the conditional label expectation, conditional on being in the set S. So it's the best constant predictor. And so the only way we kind of gotten to this point is if there's actually something in H that does predict better than a constant on the set S. And that's a contradiction because our premise starting out was that there was nothing in the set H that predicted better than a constant predictor. Okay, so we have established that not only is this a sufficient condition for Bayes optimality, it is a necessary condition in the sense that whenever I have a set H that does not satisfy the weak learning condition, then multi-calibration with respect to H can't imply Bayes optimality because here's a, in particular, here's a concrete function that you're multi-calibrated with respect to, but is not Bayes optimal. Okay, so a necessary and sufficient condition. One more theorem, I won't prove it because we don't have a ton of time, but just to sort of, I've like left this algorithm on the board this whole time because we've got, like this algorithm for computing multi-calibrated stuff. And now we've got a reason to do it. Like if you're multi-calibrated, you are potentially Bayes optimal, at least if H satisfies the weak learning condition. But we proved this condition, we proved this equivalence with respect to perfect multi-calibration. And of course, this algorithm doesn't promise you perfect multi-calibration. It converges to alpha approximate multi-calibration. Okay, so it would be a bummer if this characterization was vacuous until the approximation parameters became perfect. Like what you really want in order to get a guarantee out of this algorithm is an equivalence that carries these approximation parameters through. And you can get that too. So let me just state the theorem without proving it. Oh, one thing. Our weak learning assumption for exact multi-calibration, where we just proved this characterization, our weak learning assumption was really weak in that we assumed if it's possible to do better than a constant predictor, there has to be some H that does, can just squeak by. You can do better than a constant predictor by just, an arbitrarily small amount, right? That was enough to get the guarantee for perfect multi-calibration. If you think about it, like if you're just squeaking by, this algorithm might eventually converge to Bayes optimality, but like the progress it makes at each iteration could be arbitrarily small. So if you want a condition that's going to imply that this algorithm converges quickly to approximate Bayes optimality, you need a quantitative version of the weak learning assumption that will, and the convergence bound of this algorithm will depend on that quantitative parameter. Okay, because we need to make some quantitative progress at every round. Like the way the algorithm works is it looks at level sets. We're making a constant prediction there. It's relying on the fact that if we satisfy the weak learning assumption, we can do better than a constant on each such set if we're not already Bayes optimal there, and we're making progress there. But the progress might be very slow if we assume nothing other than the weak learning assumption we've already assumed. Okay. So here's like a quantitative version of it. So let's say that H satisfies the gamma weak learning assumption with respect to some distribution if for every subset of the feature space if it's possible to do better than a constant prediction, if the Bayes optimal predictor restricted to this level set predicts better than a constant, in fact, if it predicts better than a constant by some margin gamma, okay, then there's a function in H that also predicts better than a constant by some margin gamma. Okay. So this margin is doing two things, one of which is making the assumption weaker, the other of which is making the assumption stronger. Our original weak learning assumption, which was just this assumption with gamma equals 0, said whenever it's possible to predict better than a constant at all, we're assuming something in H can predict infinitesimally better than a constant. Here we've added this parameter gamma to both conditions. This is making the assumption worse or weaker. This is making the assumption weaker, right? It's saying if it's possible to predict better than a constant function by just a little bit, but not by more than gamma, we're actually going to let the weak learner off the hook. Doesn't have to do anything. This is making it stronger, though. It's saying if it's possible to predict better than a constant function by more than gamma, then I actually want there to be something in H that can predict better by at least gamma. Okay, again, it doesn't have to do as well as the Bayes optimal predictor, which might predict way better. Just has to do better, but by at least gamma. So it should predict better by gamma whenever doing so is possible. Okay, so this is, like when gamma is 0, this is the same assumption. As you dial gamma up, you make the sort of hypothesis of the requirement weaker and you make the conclusion stronger. Okay. And note that if we're going to assume this, there's no hope of getting convergence to better than gamma approximate Bayes optimality, because we don't require anything of our weak learner if we are already gamma approximately Bayes optimal. Okay, but like you might hope that by assuming something like this, the gamma weak learning condition, that you can prove fast convergence to gamma approximate Bayes optimality. And indeed you can. So let me just state the theorem. The proof is in the notes, but it's, you could also work it out yourself given what you've already seen. So it says fix any distribution D any model F any gamma greater than 0 and any class of functions H satisfying the gamma weak learning assumption. And let's set as parameters in this algorithm alpha equals gamma and beta equals 1 over gamma. And actually, if you notice in this algorithm, we never use alpha or beta on their own, only the ratio of alpha to beta. So it doesn't matter exactly how you set alpha and beta. What I want is that alpha over beta should be gamma squared. Okay. Then regression multi-calibrate. Halts after at most 2 over gamma squared iterations and outputs a function f t minus 1 that is 2 gamma approximately Bayes optimal. By which I mean the squared error of the function you get out of this boosting algorithm is at most the squared error of the Bayes optimal predictor plus 2 gamma. Okay, so you actually get a quantitative version of this. This is a multi-calibration algorithm, but if your hypothesis class happens to satisfy this gamma weak learning condition, actually, we don't even require that the hypothesis class satisfies it. We require that the learning algorithm paired with the hypothesis class does. So it might be that you don't have an oracle for learning over this class because it's, you know, some complicated non-convex thing. So you can't get the thing that exactly minimizes squared error. But it happens that the learning oracle that you have, although it can't exactly optimize, always improves a little bit over the best constant predictor. Okay. It says if you have this hypothesis class satisfying the gamma weak learning condition, then you can run this algorithm for only 2 over gamma squared many iterations. And not only will you be gamma approximately multi-calibrated with respect to all functions that have squared magnitude at least 1 over gamma, but also you will be within 2 gamma of Bayes optimality. Okay, so a quantitative version of this. And it is is no longer any mystery that the boosting algorithm, the theorem that allows us to prove convergence to Bayes optimality, the algorithm that converges to Bayes optimality is the same algorithm that converges to multi-calibration, because under the weak learning condition, multi-calibration and Bayes optimality are the same thing. Okay. Next week's Thanksgiving. I'll see you guys in 2 weeks.